All right. So, chapter 4, Earth, Moon, and Sky. What does that mean? So, let's see if we have, well, we don't have one of the little tables of contents. So I'll just tell you. We're going to be talking about axial tilt, really going into a full explanation of the seasons. Just like touched on it, if you remember, in chapter 2. So explaining why it's hotter in the summer in the northern hemisphere, what we call the summer, and vice versa in the southern hemisphere. Explaining what's going on with the equinox, why the equinox is a special day where there's 12 hours of sunlight and 12 hours of darkness everywhere on Earth. All right, and so to be just that whole kind of like thinking really visualizing this at different points, thinking about, what it means to orbit and be tilted. Okay. Then we've got phases of the moon. So we're going to get into kind of in a similar vein. Why is the moon sometimes fully illuminated, reflecting sunlight? Why is it sometimes invisible, right? Then we'll talk about eclipses. Eclipses being either lunar or solar. Lunar eclipse, moon goes behind the Earth, in other words, passes through the shadow of the Earth. Solar eclipse, moon goes in front of the sun and casts a shadow onto the surface of the Earth. All right. How do those both make sense? How do we represent them? And then we'll talk about tides. How does the moon create tides? Why do we have two tides a day? Why are they positioned where they are? So it's actually quite a bit of content. It's one of the bigger, more difficult chapters. So keep that in mind. We'll get through it, but be aware. Okay. So I was checking our clock here. We are good. So first of those topics, Earth's axial tilt. All right. So review question. At which position in Earth's orbit does summer occur? And obviously, the elliptical nature has been made more dramatic. So this is kind of funny because on the one hand, yeah, sure, it is a review question. Except, it's all about elliptical orbits, but it's also really a trick question. Okay? It's really a trick question. Yeah. It's three. Okay? And not only is it three, but it depends what you mean by summer. If we mean like the months, well, the Southern Hemisphere, Australia still says July, is July. They don't change the names of the months. But people in Australia, it's a good example because, English speaking country in the Southern Hemisphere, they're, they refer to, the months of, July, August as winter months, just that, of course they would. So it kind of depends. What do you mean? Are you saying like particular months or the actual season? And the main takeaway here is that in the northern hemisphere, where we all live, summer occurs when we are furthest from the sun. Okay? Which I'm sure some of you are thinking like that can't be right. I mean, we're further from the sun. There's like it's colder, right? It's because the elliptical nature of our orbit is not the reason for the seasons. The reason for the seasons is the axial tilt. The elliptical orbit is basically unimportant. It's just a distraction if this is what we're trying to answer. All right. And it's just because there's just not a big enough difference. We're not that much further from the sun because our orbit is not highly elliptical like the picture. All right. So with that review slash trick question out of the way, let's get into the actual kind of content here. So axial tilt, which shows the correct rotation axis for the Earth compared to its orbital plane. Looks like one and three are the same. What am I missing? Well, it's two. I couldn't find a difference between one and three. If anyone sees a difference, I don't know. But regardless, you can rule them out because they don't show the tilt. They show the planet, being exactly perpendicular to the orbital plane, but it's not. It's tilted. And remember that value, that tilt, is 23.5 degrees. So this angle right here, 23.5, the axial tilt of the planet. So the entire planet is tilted about 23.5 degrees from the orbital plane. All right. And so what the way this is phrased is if it was straight up and down, we would say that it had no axial tilt. All right. But this way it's tilted 23.5 degrees. Nope. Right. So it spins like that. See? So as the planet goes around the sun, it keeps that tilt the whole time. So it's always tilted the same way. And we know that because think about the North Star, right? The North Star, Polaris, is above this axis, the axis which is the rotational axis. So the North Pole always points towards Polaris. So that means that the planet can't like tilt different ways throughout the year, which means that the tilt isn't towards the sun. The tilt is independent of where the sun is. The tilt is always facing towards the same distant stars. So as we go around that circle, we keep the same tilt. Right? But here we're not showing the orbit, we're just showing the rotation. All right, well, now let's include the orbit. So this is going to kind of animate what I was just describing. So here we got the planet tilted at 23.5 degrees, right? So there it is. So this is in the picture, this would be located at perihelion. And this is actually kind of more of a accurate representation of the elliptical orbit of Earth around the sun, because notice that the focus that the sun is located at is not like super close to the edge of the ellipse. It's pretty near the center. Kind of got to look at it carefully to notice it's not right in the center, right? Well, that's more like what our orbit is actually like. But anyway, so here we are at perihelion. We have the North Pole facing away from the sun, which means that the southern hemisphere is facing towards the sun, or you could, including the South Pole. And so this would correspond to northern hemisphere winter and southern hemisphere summer. Summer because of the tilt, not because it's slightly closer to the sun. And just to come circle back for hopefully the last time to that idea, but I want to say this is that you might think that in this would be very reasonable to think it that okay, sure, we're only slightly closer to the sun at perihelion, and we're only a little bit further from the sun at aphelion. But doesn't that make some difference, right? Doesn't that sort of like maybe just like contribute to the axial tilt? Well, in that case, the summers in the southern hemisphere would be consistently hotter, wouldn't they? Because you would have the axial tilt, which we'll see means more direct sunlight and longer days, contributing to summer in the southern hemisphere at this orientation, and the planet happens to be closer to the sun at that point, right? So, which is around January to December. So there you go. Southern hemisphere summers should be a little bit hotter than northern hemisphere summers. But that's where you can say, well, no, that's not the case. And it has to do because what does it mean to have climate and weather? Well, it's all this big system, right? Controlled by jet streams and ocean currents and huge amounts of heat being exchanged over our atmosphere and our ocean. And so there's nothing that would kind of like let that happen, let Southern Hemisphere's summers be a little bit hotter. On average, there's no difference. The local variation is more important than any sort of hemisphere variation. All right, but getting back to the axial tilt, here we have South Pole tilted towards the sun. All right, so this is kind of what the sunlight would look like. Notice, right? When the South Pole is tilted towards the South Pole actually gets sunlight. Okay, doesn't get it very directly because we're getting down to the very where the sunlight's just sort of kissing the edge of the planet, right? But during this part of the orbit, right, during these northern hemisphere winter months, the North Pole clearly doesn't get any sunlight at all. See? Because it's pointing away, the sunlight does not reach it at all. All right. So then we can split between the hemispheres. So the orange represents the sunlight in the northern hemisphere, and the yellow, everything south of the equator. So more light in the southern hemisphere. If you just look at the proportion of light, all right, there's more light in the southern hemisphere when the planet is when the planet has that hemisphere tilted towards the sun. Okay, so that corresponds to summer in the southern hemisphere. Just remember, if that hemisphere is tilted towards, it experiences summer. So this is what the southern summer looks like from the point of view of incoming sunlight and the orientation of our planet's rotation axis relative to its orbital plane. All right, and here we can see an angle showing how far the sunlight extends. Okay, well, actually, it's showing the Arctic Circle. Excuse me. So it's showing the full Arctic Circle, and it's showing that the entire Arctic Circle is in sunlight, being bathed in sunlight during the southern summer. So the South Pole is getting sunlight during this time of the year. The Arctic Circle up north, well, by definition, in the most extreme case, so when we get to the time where the southern hemisphere is in peak summer, so the what we call the winter solstice, which is the December 21st solstice. Okay, so that's the longest day of the year in the northern hemisphere. It's going to be the shortest day of the year in the southern hemisphere. And what we're looking at, so I said it backwards, sorry. So the December 21st, right? So what we call the winter solstice is going to be our shortest, our being northern hemisphere. It's going to be our shortest day of the year. It's going to be their longest day of the year. And it's going to be a day where the Arctic Circle for sure is going to get no light, simply no sunlight at the winter solstice, the December 21st solstice no sunlight is going to get to the Arctic Circle. And it's not just that day. It's actually the Arctic Circle goes all the way down to where there's at least one day out of the year, that's the limit of the Arctic Circle, where the sun never sets, and one day out of the year where the sun never rises. That is the defining characteristic. That is the edge of the Arctic Circle. And then everything north of it is going to have more days of perpetual darkness. So as you go further and further north of the Arctic Circle, you get, say, 1 week where the sun never rises. And likewise, 6 months later, you get 1 week where the sun never sets. And the exact same logic will apply to the Antarctic Circle, not circus, around the South Pole. That's by definition, that's how the Arctics are defined. Okay. So now let's go over to 6 months later, halfway through our orbit around the sun. Now we're at aphelion, pretty close to it, because you might think it's a weird coincidence that, that these 2 points, correspond to aphelion and perihelion, the points where the tilt is most extreme. It it hasn't always been that way, and 100,000 years from now, it won't be. The planet kind of goes through the orbit of the ellipse goes through a precession around the sun, and that just happens to be where we're at right now. All right, but anyway, you're not responsible for that. Just interesting fact. The North Pole tilted towards the sun. Okay, that of course is going to be the northern summer. Here we split up the sunlight in the same sort of way, showing that most of the sunlight goes to the northern hemisphere in the northern summer. Right? More light in the northern hemisphere, summer in the northern hemisphere. Northern summer. Notice the Arctic circles again. These are going to be days of perpetual sunlight, days in the Arctic Circle where the sun never sets. Okay, so those are the two cases correspond to multiple points, but the extreme points being called the solstices. Okay, so this, and just to make sure we're clear on which one is which, this would be the solstice that occurs in um, well, June, the one we're coming up on, June 21st, the longest day of the year in the northern hemisphere. And then the summer is going to be December 21st, which of course is the northern winter. Okay, so other points in the calendar and also other important concepts with the amount of sunlight that's hitting the planet. Okay, so now we're going to have a point in our orbit where the planet is neither tilted towards or away. And there would be lots of middle, tilts, because there'd be the extreme tilted, northern hemisphere, North Pole tilted away case where my cursor is right now. Let me use a laser pointer thing. Okay, so right there. And then as we continue to orbit in our counterclockwise direction, we would get to points where you could say, yeah, we're still tilted away, but less so. Why less so? Well, because our tilt, instead of being tilted straight away, which happened, at this point in the orbit, now some of our tilt is not away from the sun, but sort of what the term is tangent to the perimeter of the ellipse. So it starts to be that the tilt is in a different direction relative to the path of the orbit and also relative to the velocity, right? Because if you think about the planet, it has, our planet, it's got a velocity, which is, right here. This is how it's moving. So this would be the instantaneous velocity, the speed of planet Earth through space at this moment in its orbit. Okay? So at this point, it's hopefully clear that the tilt is neither towards nor away. The tilt is entirely in the direction of motion. So that means that we're not going to have a effect of different sunlight. We're not going to have more sunlight in the southern hemisphere or more sunlight in the northern hemisphere. No, we're going to have shared sunlight. And it happens at the point that I showed first, in front of the sun and mostly hidden but clearly visible. We can see it happening again 6 months later on another point and behind the sun. So at both of these, the tilt is neither towards nor away from the sun. Okay, so in these cases, we call the light hitting the Earth the equinox, and it's exactly equal. So you might be thinking like, wait, why did half the planet turn orange? Well, because remember how the other animations showed the sunlight either coming from the left or coming from the right, and there's that spreading cone, which represents the way that light diffracts and spreads out to fill in space, property of waves, including light waves. Well, now where's the light coming from? Well, in the case of the um, what would be, I see, because we had the northern hemisphere pointing away. So the one in front, the one where I drew the velocity vector, would be the spring equinox, And the case where the planet is kind of mostly hidden by the sun would be the fall equinox. And so in either case, the sunlight is either coming out of the screen or going into the screen. So we could think of this tilted planet maybe representing the fall equinox and the sunlight just kind of coming right in, from you as the observer and hitting the planet head on. And so then it's equally the amount of sunlight will be exactly equally shared between the two hemispheres. Sure, there's still a tilt, but the tilt is not relative to the direction of light. It's 90 degrees. It's perpendicular to the direction of light. So the light's just going to hit the planet head on. And that's what this is showing. It's exactly equal light in the northern hemisphere compared to the southern. They share the light. So because of that sharing, that equality of light, that these days are known as the equinoxes. So it's got that same root, equal, equality, equinox, equal light. All right. So all that great start, but we're going to elaborate on the idea a little bit because it's one thing to say tilting towards the sun creates, a warmer season. But it's another thing to really kind of dive into why that is. What about tilting towards the sun makes for warmer weather, hotter days, more intense sunlight? Well, that's what we want to discuss. And the way I often think about it is that you've got just longer days when the tilt is in your hemisphere is towards the light. That creates longer days. Well, that's going to allow things to warm up more, right? If you have more hours of sunlight, you've got, more heat coming in, coming into your system. But it's actually more than just that. If it was just the length of the day that changed, yeah, that would cause some change in temperature. But it's also going to be the amount of sunlight per square area. And that's the concept that we want to make sure we understand because it's a little bit harder to wrap your head around at first. And that's what we're going to start with, visualizing the sun angle. So step one, locate your latitude. So let's consider Eugene, Oregon, not too far from the San Francisco Bay Area, fairly similar latitude. Eugene being 44 degrees north. Now let's imagine the sunlight coming in as a bunch of parallel arrows. They're all pointing in the same direction. That's part of the reason for that. And it may just make sense to you. Yeah, sure. Sunlight comes from the sun. It should just all come in as a big wall of light. And if you're not sure that makes sense, that sunlight should come from the sun, it's just a big wall of light. The actual reason for it, the explanation is because we're so far from the sun. Because when you have a source of waves, a source of light waves, if you're really close to it, you have to actually worry about the angle of those waves as they spread out from the source. But when you're really far from a source of light, you can consider the light as approaching you as what are called parallel waves, or just a set of parallel waves. And that's how light gets to Earth, because of course the sun is very far away. Okay, so now we can consider a plane, because we're going to be thinking about angles here, to represent the surface at Eugene. And to do that, all we've done is just drawn that tangent line at the point of Eugene on the circle of Earth. And Earth being a circle here because we've taken a cross section. Okay. All right. And the tangent line is the line that kisses the surface. It just touches at a single point. The other way to think about the green line is it's perpendicular to the radius. So the radius is this black line connecting the center of Earth to the surface where Eugene is located. And if we made a right angle, a 90-degree angle, then it would meet the green line, the tangent line. Okay? So now we're going to include axial tilt in our consideration. Because right now, we didn't. This is like some hypothetical Earth. Initially, we didn't. This is like some hypothetical Earth with no axial tilt. Okay? But of course, that's not the case. So we have to decide what time of year are we considering here. All right? Are we considering a a time of the year of northern summer or southern summer? Well, northern summer, as the parentheses specify. So as we do that, we can kind of, and it's kind of, I think it's sort of like gratifying to see it happen. We see this surface representing the land at Eugene tilting towards the sun. So it's like, oh, okay. So it's kind of like it's lining itself up for a direct hit of the sunlight, right? So here the sunlight, or you might, it's obviously not exactly direct, although you could be at a different latitude and get it exactly correct. And that's a whole thing that there are latitudes where you can get direct sunlight. Okay, those are the tropics, by the way. Okay, but back on track here. We got the sunlight coming straight, almost straight in, gonna hit Eugene, and the angle that it hits at tells us what is the, specifically the degree of the sunlight from the vertical direction. So how directly overhead the sunlight is going to be on, at this particular northern summer day, at this particular latitude, the sunlight would come and it would be hitting the ground at 21 degrees from vertical. So it's not like the light is coming from directly overhead. There would still be shadows, for example, because if your sunlight is coming from directly overhead, you don't have your typical, lengthened shadows. You'd only have shadows directly under things, right? Which is kind of unusual lighting. But in this case, it's fairly straight overhead, right? So it's like, the sun, what would feel, and you just sort of like anecdotally really intense light, right? If the sun is like, high up in the sky, it has a noticeable effect on kind of how you experience sunlight. All right. So this is sun bathing these dogs in sunlight, right? They're basking in the sun because it's a summer day. Okay. Sunlight coming from almost straight overhead. This is the visualizing the sunlight angle. We can see it coming right down. Okay. So there, this is the angle. So, this would be like exactly overhead. So in that case, the dogs would have to be in the tropics somewhere. But if we assume that they're at, Eugene, where the sunlight never comes from straight overhead, well, then the angle relative to the vertical was this one. Let me show you the 21. Okay, so where do they get the 69? Well, that's the angle relative to the ground, which is just 90 minus 21. 90 minus 21 is 69. Just a different way of showing the same thing. Okay, so the sunlight's coming from nearly straight overhead. All right, so in other words, the sun's altitude at the summer solstice is 90 degrees minus your latitude plus the axial tilt. Okay, so that's kind of interesting because it reminds you, hopefully, of the formulas that we saw in chapter 2, where we dealt with stars with known declination, and we were able to relate those to our latitude by knowing the altitude of that star in the local sky. Well, here it's pretty similar, right? Except now we need to have a particular day of the year, so we know that the sun is as high as it's going to be. And we also need to account for the axial tilt, which we didn't when we were talking about stars. And that's because, well, with the stars, it didn't matter because we just pointed to them and they were all relative to our planet. The celestial sphere, if you remember, had poles that were lined up with our poles. So the celestial sphere itself is tilted by definition. That's how it was set up. That's how people created it and defined it and work with it. But when we talk about the sun, well, the sun is all relative to that. So when we use the sun to find the angle, right? And or in this case, find the altitude, or if you knew the altitude, you could solve for your latitude. Notice that, right? You could because this is an equation. This is sun altitude. I know it shows it as a colon because it's just showing it's like, hey, this is how you would find it. But you could replace that colon with an equal sign and algebraically solve for your latitude if you knew the altitude of the sun. How would you know the altitude of the sun? Just measure it, right? In this case, just, find out how high it is, use a protractor or a sextant or something and find out how high above the horizon the sun is located, 69 degrees. All right. And then you could use that to calculate your latitude. Or again, if you knew your latitude and you just wanted to know how high the sun is at a particular day, namely the summer solstice, because that's what this applies to, then you could plug in your known latitude and find that maximum altitude. Remember, altitude in this context is an angle. It's not altitude like, sometimes we talk about planes flying at altitude where that's a distance measured in meters. The term is used that way, but when it's used for sky observations, it is an angle, and it varies between 0 at the horizon and 90 at the zenith. This is a reminder. Okay, so now, all right, northern winter. Same point, still Eugene, same latitude. We can see right away we're going to get some less direct light, right? Because in northern winter, Eugene isn't, kind of mostly facing directly into the sunlight. Now the surface of the land is kind of turned away from it. So when the sunlight hits it, it's going to hit it at that sort of obtuse angle, right? It's going to come in low. All right. So we have the sunlight coming in 67 degrees from the vertical now instead of 21. That's a very big difference. Sunlight directly overhead or, 21 degrees off of directly overhead versus, pretty darn close to the horizon, right? So not directly overhead at all. Okay. So now we got our same dogs trying to warm up in much colder weather. We see kind of the long shadows being suggestive of the time of the year. And we got this little yellow arrow showing the sunlight coming in at that low angle. All right. And just as before, this figure shows the angle of the sunlight relative to the horizon, which is, kind of a complement to this measurement, which is the angle of the sunlight relative to the vertical. The sum will just always be 90, just two ways of thinking about the same thing. Same formula, sun altitude, 90 degrees, minus the latitude, minus the axial tilt. Well, I shouldn't say exactly the same because notice the difference. Instead of plus the axial tilt, it's minus. Why the difference? Because we've gone from one extreme, the summer solstice, to the other, the winter solstice. And the difference is just a difference of subtracting the axial tilt instead of adding it. And that should make a lot of sense because you add the effect in the summer to make it a bigger altitude, make the sun higher overhead, and you subtract the effect of the axial tilt in the dead of winter to make the sun lower. And if the axial tilt wasn't there, then you wouldn't have that addition or subtraction. So you can really kind of, I think that the formula, the expression, right, helps sort of illustrate the concept. Okay, now all of this is crucial, but this kind of reminds me of what I said a minute ago. It still leaves some unanswered questions if you want to maybe quantify it, right? So how do you say like, okay, yeah, sure, light coming from straight overhead is going to feel more intense, but is that good enough for a scientist to say like, it feels more intense, it feels brighter? Well, no, you really need to make sure that there is a quantifiable way, a measurable way to talk about why sunlight coming from straight overhead actually is hotter and delivers more energy. And it comes down to this concept of energy flux. Also, you could call it light flux because in this case, the energy is being carried by light. And this is what I said when I said, or what I meant when I said we're going to talk about the energy per area, or we're going to talk about the sunlight per square meter. This is it. Okay. So introduces a formula. Hopefully, it seems like a simple one. You can see it's just a straight ratio. I know it's got a weird Greek letter in there, which is phi, but that's just a term, just a letter that's chosen to represent flux. All right. And flux is just it. Think of it as just a term that gets used for like the amount of something that passes through. So flux is all about like it's a rate of change and it's dependent on area. So it's like how much of something passes through a membrane, a door, a gateway, or just open air. And so flux is all about like, and if that's how we kind of use the term. It I know it's not a term that gets used that much in everyday language, but when it does, it gets used in a similar way to its scientific definition. Scientific definition. Um, if it does help you think about it, it's power per area. So power like wattage and then per area. And and then so in it's and then power itself is energy per time. Okay. And actually here, it so that's a oh that's actually interesting. So the I didn't mean to contradict the slide, but there's a lot of kind of like different ways to what you want to define. And anyway, I should have noticed that they're talking about energy flux. And so energy flux is energy per area, not power per area. Power per area is often called intensity. Um, and then here they're calling it energy flux. The terms do get used interchangeably, but most important is that it just matters what you want to focus on. And so here it's the energy delivered by the light, which of course would take a certain amount of time. Because I mean, think about sunlight, right? That if you want to talk about the energy that sunlight can deliver, well, you need to know how long. If I say, hey, if I put a jug of water out in the sun and I want to say how much energy does it receive from sunlight, well, the follow-up question to that would be, well, how long are you leaving it in the sun? Because if you leave it in the sun for an hour, it would receive an hour's worth of sunlight, okay? And the hour's worth of energy delivered by that sunlight. So energy does require a known amount of time. You're totaling it. So that's why sometimes we talk about power, but of course, that's not what we're doing here, but sometimes we do. And with power, then we that's just energy per time. And that way you don't have to know how long, it's just a rate. If you put something out in the sun, well, it's going to receive energy at a certain rate. That's its power, the power that the sunlight is delivering. And it's instantaneous. Okay, but back to flux. So a higher flux of sunlight hitting the surface of the Earth causes warmer temperatures. So if there is more energy per area, things get hotter faster. Okay? So increasing the area, will it make the flux go up or down? So if I have a fixed amount of energy, so sunlight, right? Coming from the sun delivers a fixed amount of energy, and which fixed I mean unchanging. And I make the area bigger, will flux go up or down? Okay. Yes. Yep. It will go down. Very good. Thank you for answering it. Yep. Yep. Nice job. Camila, Alara, Alexander. All right. So because it's a inverse proportionality, that term keeps coming up, right? And you're spreading it out, right? You got the same amount of energy, but now you're spreading it out over a bigger area. It's kind of similar to like, paint, right? If I have a certain amount of paint and I spread that paint out over a bigger area, I'm going to have a lighter cover, right? It's going to be a lighter covering. But of course, if I concentrate it on a small area, then I can have a really concentrated covering of paint. So that's the same idea here. So flux is proportional to the inverse of area. Flux is inversely proportional to area. So, won't do the lab, but I love these figures because it just, this is with a flashlight. But if we think about the energy flux hitting a surface at different angles, you can just really see how that calculation would be made. You've got, a certain amount of energy coming from the flashlight, and then when that flashlight is hitting at a certain angle, well, think about this being like the beam of light. If I was to make the angle bigger, well, that whole beam gets elongated. And now it's the same, it's the same battery in the flashlight, the same amount of energy coming out, but now it's being spread over a bigger area. So if the energy is coming from straight overhead, then it is as concentrated, and energy here being energy of sunlight. If that energy of sunlight is coming straight overhead, it's as concentrated per area as it can be. Because if it comes in at an angle, then we have a spreading. Notice the size, right? this is the smallest rectangle. And here the opening is just to sort of think like, okay, if we were to restrict it, just consider a certain amount of it. Because it's of course, sunlight's all over the planet, but well, to answer the question, let's just visualize, one restricted piece of that incoming light. So here, right, not straight overhead, but still fairly steep. And we've got this now kind of elongated parallelogram shape, and it is just bigger. It's a larger area. It has to be. All right. And it comes down to geometry. You could find out exactly how much bigger it is. Okay. And look, if it's even at a larger angle relative to straight overhead, now that sunlight is spread out even more. The flux has decreased in the three cases I've shown just now. We went from maximum flux to smaller and smaller flux because in each case the energy was unchanged. It's all the same sunlight, but the area increased. Right? So at all three angles, the same amount of energy is in the light, but the area that the light illuminates is larger for the shallower angles. Therefore, the energy flux at the surface of the table is different. It goes down. Ah, I got to try fixing that. So we end up with a relationship where the angle changes it. And you're not going to, it's not a big deal that there's this weird formatting error with the formula, because I will not ask you to work with it because I don't want you working with any sines or tangents or anything. But this is just illustrating that it is dependent on the angle. And if you are familiar with trig functions, you kind of think about how that area is calculated. And A naught, by the way, would be the area when it's straight overhead. So think of it as the maximum possible area. But as the angle gets bigger and bigger, you're dividing by this value. And the whole deal with sine is that it approaches one as you go from 0 to 90. And that's how we're, in this case, we'd be measuring, from 0 being straight vertical to 90 being, sunlight just like coming from the horizon, so barely any sunlight. And in that case, you'd be dividing by a number that is getting, progressively bigger. So you're, dividing by, which d is going to be, let's see, well, sine of the angle. So sine, yeah, yeah. So you be dividing by something that is so 0. No, I'll have to think about it. So the angle. Oh, okay. I was like, yeah, that can't be right. So it's the angle relative to the horizon. Yep. So it's the opposite of what I said because you're dividing by something that's approaching one. So that's why when the angle is really small, I take sine of it. You're going to get something that's close to 0. You divide by a really small number, you get a big area. But as I said, I will not ask you to do that calculation. Although I do have homework problems to ask you to calculate flux, but there it's all algebra, arithmetic. Okay, and that's a good stopping point because it really covers the key idea that, and just to sort of paraphrase this, that in those summer months where the sunlight is more direct overhead, you're getting more energy per area, a greater energy flux. And that really is what makes that type of sunlight, that type of season hotter, is the concentration of sunlight per area. Okay, so great stopping point on chapter 4. Obviously, still a lot to cover. As I said, it's a big chapter. All right. Let me stop the recording for now.